This session is ArcGIS API for JavaScript, fundamentals for building 3D web apps. My name is Javier Gutierrez. I'm a product lead of the JS API 3D, working on the Esri R&D Center in Zurich, together with Thomas Otter. We are very excited that you're here. Thank you very much for spending your time. And if you want to go ahead and check out the slides yourself, they're hosted on GitHub, so you can do so yourself. You can see the URL here. All right, let's get started. Important note about this session, this is about the fundamentals of 3D in the web using the ArcGIS API for JavaScript 4x version. And I want to stress out that this is about the fundamentals of the API. So if you're already familiar with it and you already built a few applications, then this session might be a little bit of a repeat for you. But if you are new to 3D, even if you already are familiar with the JavaScript API, this is the place to be, because we will kind of go through all the important 3D concepts. This session is obviously also about writing JavaScript and HTML. So if you're new to it, then I think you will be able to follow along nicely. Let's get started. The agenda, we will cover some of the introduction topics related to how to get started with the API, where to get the data, how does it fit within the Esri ecosystem. Then we'll go through creating a small example of a 3D app, and we'll dig a bit deeper into the concepts of the API and how to work with the 3D SceneView and highlight some of the latest features that we have released recently. So let's talk now a little bit about the ArcGIS 3D platform. So you can see in the core, we have the ArcGIS Online or ArcGIS Enterprise, which is equivalent for on-premise installations of our Esri cloud, Esri hosted cloud. The Esri cloud, the ArcGIS Online product contains and provides a huge amount of online content and services available to you. You can also obviously upload your own content. To upload such 3D content, you will need to use ArcGIS Pro or CD Engine, as we see here on the left. To consume this content, either on desktop devices or on the web, there are certain 3D applications that are already available out of the box. Obviously, you can consume as well with ArcGIS Pro and CD Engine, but on the web you have available the SceneViewer, which is the main application for creating and visualizing web scenes. The story maps, which allow obviously 2D maps, 2D web maps to be added to stories, but also 3D scenes. And the web app builder, which offers more customizable experience to create 2D or 3D applications. These out-of-the-box 3D web apps look like this. As you can see, the SceneViewer, story maps, and web app builder. But what about the API? How does it fit within the story? Well, the API is actually used to build these 3D applications that you see here. It is a core component of our 3D platform. As you can see, it is used for building these 3D apps, but it also allows you to building your own apps that interact and integrate very well with the platform using the services, but also using other capabilities like authentication, security, and user management of the platform. Some custom 3D web apps that you might need to build might include social feeds, reporting functionality, custom UI elements. Here you are in control, so you can add as much or as little as you need. The 3D API provides you the view and provides you a lot of interactivity and tools to interact with the view and with the data. But on top, you can use any existing HTML technology that connects with the API. Here's the entry point for you for working with the JavaScript API. That's js.arcgis.com. This is the SDK page where you can find a lot of information about the API, about versions, about what's new, about how to use the API, and guides and tutorials. There's a lot of samples. We have over 200, if I'm not mistaken, already, and all the API reference documentation. So what is the ArcGIS API for JavaScript? How would we define it? The API provides you with visual mapping components and widgets in 2D and 3D. It supports various different layer types or data sources and integrates well with the platform. As I mentioned, you can get it from the website js.arcgis.com, either pointing directly to the CDN or downloading as a zip file or using npm to build your application with Node modules. Let's quickly go over the desktop browser 3D requirements of the JavaScript API. What we recommend is that you have modern hardware with a graphics card, either integrated or dedicated. The dedicated graphics card will always have better performance, but it is not required. An integrated graphics card should be able to handle and render most of the web scenes that we see today with pretty good performance. If you see problems like stutters or your scenes are not performing very fast when you move from slide to slide or location to location, then it might be time to invest into a dedicated graphics card in your machine. We support the 4 latest web browsers with WebGL support: Chrome, Firefox, Safari, and Edge. We recommend that these are up to date with the latest versions of the software. And Internet Explorer is also supported, but it's not recommended given the lack of support from Microsoft. Mobile browsers are also supported. So if you want to see your web scenes and your applications in a mobile phone or a tablet, you can also do so with the ArcGIS API for JavaScript. As you can see here, these are the models that are officially supported with Safari browser and Chrome browser for each of the iOS or Android platform. However, other devices and browsers might work. We don't test all of them in our team, but we have seen in our experiences that modern devices with more than 2 GB of memory should be able to run all the 3D applications without issues. So let's talk about data. How to get and which types of data can you get into the 3D JavaScript API. It's very important for you to know that 3D JavaScript API does not only work with 3D data, it also works with 2D data, with your existing feature layers, map layers, tile layers, and even your raster elevation. These are the base layers of any 3D scene, and they are very, very important. We can leverage all the attributes and symbology, labeling characteristics of all these layers in 3D as you can in 2D today. However, if you want to bring 3D content in your scene, you will be looking for scene layers, which are based on the open standard I3S. These are several data types: 3D object, which is used for representing cities; integrated mesh, which represents a continuous mesh scan from drones or planes in 3D. Point clouds, which is a data type coming from LiDAR scans. Point, which is large quantities of point data. And building scene layer. This is the latest data type added to our collection of 3D data types, and it supports BIM data coming from Autodesk Revit with information about the building interiors and design of the building structures before they're constructed, including detailed representations of parts of the building like window frames, doors, even electrical sockets and plumbing fixtures. So how do you get content for your apps? Basically following the same pattern that existing 2D layers in the ArcGIS platform follow. You load the data into a desktop application, ArcGIS Pro City Engine. You publish it to ArcGIS Online or Enterprise, which is where the layers are hosted. And then you can read them with the JavaScript API or JavaScript API-based applications. And yeah, pretty simple. How do you do this in Pro? Well, when you add a layer to a TOC, for example, a 3D layer called buildings, you can right-click on it and then go to the sharing and then sharing as a web layer. This will share as a single layer that you can use in your applications. However, you can also share it as a web scene. So you can add 2 or 3 or any layers that you need, change the base map, change the camera position, and then share the whole configuration as a web scene. And what you see in your content is the creation of multiple layers and the web scene item. This is the fastest way to get the map that you see on the desktop published and consumed on the web without a lot of effort on your side. We have been talking quite a bit about the web scene, and we haven't explained what it is yet. So what is it? It's a serialization document. It contains information about the layers, about the symbology and labeling about the environment, like what time of the day it is, do we have shadows enabled or not, what are the slides, the camera positions. It contains basically everything that defines what the 3D map is and what it looks like at any given point. This serialization document is stored in ArcGIS Online or Enterprise, and it can be read and written by the ArcGIS platform, either from JavaScript or JavaScript-based apps, or from Pro, or even from mobile devices and native applications. There are two types of web scenes, global and local. But let's quickly talk about coordinate systems before we jump into global and local scenes. Scenes support one coordinate system per web scene. So what this means is that all your cache data, so your tile layers, your scene layers, they must match the defined system, whichever you have, whichever you need. And feature and dynamic data, as you know, it projects on the fly. Either feature services or map layers, they are reprojected on the fly by the ArcGIS services. So these can be in any of the projections that are supported to be projected to the scene projection. So again, I was mentioning global and local scenes. What is this? What does this mean? And how does it affect coordinate system discussion? Global scenes allow you to visualize data on the globe, as the name indicates. They contain full extent of the Earth. You can create global scenes like this that represent global data, and you can see zoomed out all the way to the globe, or you can get very close to the ground or just to the regional level. Global scenes support three coordinate systems: Web Mercator, WGS84 or Geographic Coordinate System, or China Geodetic Coordinate System 2000. Local scenes, on the other hand, they don't represent the data in the globe in a spherical way, but rather on a planar way, like you see here. The projections supported by local scenes are Web Mercator and any other projected coordinate system. They don't support geographic coordinate systems, but they do support all the projected coordinate systems, any that you need. It is recommended that when you use local scenes, you clip the scene to your area of interest, because it makes it better for performance, but it's also easier to navigate when your scene is clipped just to the region of interest that you're working with. The last information I wanted to share about the web scene is that the specification of the JSON document is an open standard, and it's shared in the developer's website along with the JavaScript API SDK. Let's finally talk a little bit about code. So let's start creating our first 3D app. The steps are 4, pretty basic: create a basic HTML page, load the API, add the web scene, and done. So how do we create the basic HTML for our first 3D app? As you see here, we need to follow the basic HTML format, adding the doc type, starting the HTML document, and then dividing the document into a head section and a body section. In the head, we have to add a charset, and here my first line of my custom app is linking styles or a CSS file, which contains custom stylization for my application. This is not very crucial at the very beginning, but it is important to note that you will have to give the 3D view a size. So you will have to set either if you want your view to take the entire space of the screen or not, if you want maybe half of the space. The next line highlighted here is the title of the application, so very simple. And then inside the body, there are two blocks. The first is a div with an identification called viewDiv. This is where our map, our 3D scene, will be rendered. And then the second one is the script, and that's the JavaScript code that will make the application run. Okay, so now I'm highlighting how to load the API. Again, inside the head section of the HTML, I need to add these two lines. The first one is going to link to the CSS or the styles of the JavaScript API. These are important for representing the widgets of the API. The second one is the main component of the API. That's the JavaScript API itself. Here you see this URL is pointing to the ArcGIS CDN, and it's selecting the 4.15 version, which will be released a couple of weeks after this recording is made. The next step is loading modules. So now I'm working inside the script tag, inside the body element of the HTML, and I'm gonna use require construct to request two modules, a WebScene and a SceneView. Now we load the WebScene. To load a WebScene, either published from ArcGIS Pro or created with the Scene Viewer, all you need to do is call new WebScene class and point to a portal item. This portal item is referred to as an ID. And where do I get this ID? You might be asking. When you publish your WebScene to ArcGIS Online or you save it with the Scene Viewer, you can go to the URL of the item page, and you will see the ID here in the URL. So you can just copy that whole number, the whole string, and then paste it in your code directly there. The last step is creating the view. This is the component that will actually render your WebScene on the HTML page. That's called the Scene View. You connect it to the container, which is the div that we saw before in the code. That's up here. And then you connect the WebScene. That's the scene that we created right before. With that, your 3D application is ready to go. As you can see, the application loads. With this few lines of code here, it's going to load the WebScene that I created before in ArcGIS Online in the Scene Viewer, which contains all the buildings in Manhattan, and they're symbolized by the different energy score rating. The application is fully interactive. It supports pop-ups, it supports symbology. It has a few widgets, like for zooming in or the compass. And yeah, all I need to do is add a few lines of code and point to a WebScene item. However, this is not everything. As you can imagine, there are a lot more tools and properties to learn from the API. So I'm going to pass it on to Thomas to talk us through them.
Thank you, Javier. I would now like to talk a little bit about the core concepts of the API. As Javier mentioned, the API revolves heavily around platform concepts, most prominent member being the concept of a layer. A layer holds a particular set of data, for example, points or polygons or point clouds or mesh data. A renderer is a property of a layer that can be defined at runtime. It holds instructions on how data should be partitioned for visualization and how each partition should be visualized by attributing it to a specific symbol. And finally, that symbol then describes how a particular element should be visualized in detail. Should it be an icon? Should it be a cylinder? Or a 3D model of a car, for example? Naturally, there are differences between our classical 2D map representation and a 3D scene. Whereas both might support visualizing a particular data point from the layer as an icon, for example, the 2D map cannot show a 3D model as a representative symbol. This is where the views come into play. They derive the rendering technique and set constraints on visualization methods that are available for a given layer in that particular view. So in general terms, you can think of 2D map view and the 3D scene view as different manifestations of your shared data model, the map, containing the layers that we would like to work with. To illustrate this shared data model, I've created this small snippet which renders and links one map to 2D and 3D. So in this snippet here, I create a new map. I tell it to use the streets base map, which is not correct, excuse me. In the visualization, you actually see the satellite base map layer. And then I add a feature layer of the United States, and I create two views, one on the left, which is a map view, the classical 2D view, and give it that map, and on the right, I create a 3D scene view and give it the same map. And I've linked these two layers together so that if I move one thing, the other one moves too. And you can see that we are kind of looking at the same data from two different perspectives, namely from 2D top-down and 3D, where you can actually tumble the camera as you desire. All right. Across the API, you will find that most properties of any given class can be passed to a constructor in a JSON-only representation without the need of calling sub-property constructors to create that property. So this map here in the scene view, as we've seen in the example before, it's actually a map object, but with this way of declaring it as a JSON only, where we just tell it a property of base map, we can avoid having to write long chains of constructors. This concept is called autocasting, and it simplifies our lives as developers since we can declutter that object creation code substantially. Next thing I would like to talk about are object properties. The API implements an observable pattern for all of its classes, which internally is implemented through setters and getters. This allows you to decouple certain logic that is primarily depending on a particular property and react to changes in that property. So in the snippet here, what we're doing is we say, hey view, I want to watch your property, which is called center. And whenever that property changes, I want to execute this callback. And in this callback, we do not much more than just print a log message with the new center. So we can see that currently the center is at long lat 8 and 46. And if I push this button, we'll switch to a new center. Let's do that. And we see that this guy down here got updated by this watch that triggered once we changed that property called center. One of the fundamental aspects of web development is the fact that a large amount of functionality is happening asynchronously. I'm sure you're all familiar with the long callback chains we were using not so long ago, and the difficulties of understanding and handling the flow of applications throughout these callbacks. Promises amended those shortcomings by wrapping those callbacks and by providing error handling for each step in the asynchronous chain of program flow. There is then no surprise that the JavaScript API is making use of them heavily. So all of our asynchronous operations are modeled as promises, which are chainable, and many of our classes expose promise-like structures through some of their methods to signal readiness of a certain instruction. So just to give you an illustration of such a promise chain, we have a view. When that view is ready, we try to load some layer, which then executes a geometry service projection call, which then, once we have that projection, tells the view to go to that projected position. And then once that view go to, which we'll touch on later, is finished, we are in here and we are actually ready to execute the next step that we would like to execute. All right, this brings us to the data model used in the API. Let's quickly take a look at the fundamental unit, the layer and its capabilities, amongst them filtering and querying. So the list of supported layers is quite large, and one can easily get lost in the vast amount of capabilities that they provide. In this session, we'll reduce the number by focusing on those layers that are exclusive to 3D scene views and explore some of their properties. So in particular, those are the elevation layer, the scene layer, integrated mesh layer, point cloud layer, and building scene layer. So adding a layer, as we've seen in Javier's example, the API provides quite powerful and short methods of acquiring data from a server. Adding, for example, a scene layer of New York can be done in a couple of lines. So we've seen the SceneView construct a couple of times already. And now, additionally, we load a layer by URL, which is a scene layer, and we just add it to our map collection. As one of the core 3D elements, the scene layer allows you to use a 3D datasets that support filtering, querying, and various visualization techniques that you can choose from. Let's take a look at server-side filtering. By using a SQL-like expression, the server can be instructed to only return partial subsets of all the available data. And by using server-side filtering, you can not only reduce the amount of data being processed on the client, but also the load on the network, thus obtaining a better performance. Additionally, it allows you to provide different interesting aspects of your data. So for example, here we set the definition expression, which is the server filter instruction, and we tell it to only give us construction years before 1900. Let's apply that to this data set, and then we can see New York was much smaller according to this data set, or let's say more sparse according to this data set back then. And we can reset that definition expression and look at all the data again. And we can also just change that expression and say, hey, I want to see all the data that exceeds a height of 300. And as expected, we get the tall buildings back. With client-side filtering, you can obtain similar results. And while more data needs to travel through the network, a change in the filter requirements can be applied much faster, since all the data is resident in the client memory already. So in this snippet here, we have the same setup as before. We have the scene layer, we have a scene view, and then once we are kind of ready to process the data with the layer view, meaning that the layer has acquired a view, then we can create a new filter. And for the geometry of that filter, we use a polygon, and I won't go into details of how to create that one. And we tell it that we want to query all or filter all the geometry that is inside, that's contained in this polygon. So let me create that polygon here. And you see now we're only looking at a subset of the data. And we can quickly clear it, and it's instantly back. And similar to client-side filtering, the client-side querying mechanism allows you to extract data attributes from a selected subset. This information can be used to drive certain features of your application, for example. So the setup, the same as before. Now instead of setting a filter, we tell the layer view that we want to create a query, and then we set the query to the same geometry as we had before, and then we execute the query, and once we have the results, we show them. So let's do that. Let's create a polygon again. And in this example, we highlight the queried features, and we provide a short rundown of parameters that are available inside of the selected area, namely building year and the building material. And if I click on a building outside of this query, I get this attribute list in the pop-up, and it shows me all the attributes that are available, and we're just picking a selected number of attributes to drive this visualization here. And just like with many other layer types, the scene layer supports changing aspects of its visualization through its renderer property, allowing you to find the best possible visualization for your use case. So we're in New York again, and by setting the render property um, of type simple, we tell it that we want to use this symbol on all the buildings. That's what simple says, use just one symbol across all of the data. And it's a mesh symbol because we're dealing with mesh data, and we just fill the mesh area with a specific color. Let's do that. See how it looks like. So we fill it with a greenish transparent uh, symbol. And then we can also use the same simple renderer with visual variables. And visual variables is a concept that allows you to map certain attribute ranges to, for example, colors in this case. So we say we want to change the color according to the construction year. And then I won't go into the details of how it's exactly built, but let's apply that. And here we can see that there are different years where these buildings were built, and according to their color, we can get an idea of how the distribution looks like. For certain data sets, it is desirable that it can be visualized alongside data that is on or above the surface. In some cases, the user should even be able to navigate and explore the subterranean data set. This can be achieved by setting the ground opacity and the navigation constraints. So the map has a ground property, and that ground property has an opacity property, and let us set that. And then suddenly we can see through the ground. If I try to go underground, it's still not possible at this point. But if on the ground I set that navigation constraint property to type none, then suddenly I'm able to navigate underground and explore my data set from a new perspective. So to sum up the data model, we have a map object that contains all the data we would like to visualize, as we've seen before. And certain 3D specific properties of the map, like, for example, the underground properties, are available through a 3D specialized map, which we call the WebScene. It allows you to store a complete representation of a 3D scene, including layers, viewpoints, and many more properties. And this image down here kind of gives you the separation. So the web map is the 2D specialized version of the map that then gets kind of passed on to the map view, which creates the view representing all that data, and the web scene is the 3D specialized version of that map, which gets passed on to a scene view, which creates the 3D visualization of the same base data set that's contained in the map, and then map view and scene view both can handle specialized values that only apply to either 2D or 3D use cases. So now we transition into the viewing. That is how we can explore our data in 3D. I would quickly like to talk about cameras, pop-ups, and widgets in this section. So the scene view has many interesting properties that can be used to interact with your data. Amongst them are the aforementioned camera and navigation instructions like go to, interactive elements like map to screen conversions, and vice versa. In 3D, it is not enough to specify a viewpoint by its three-dimensional coordinates alone. We also need to know in which direction we should be looking. This is done by specifying the heading and tilt. So heading 0 would be looking towards north, heading of 90 degrees east, 180 south, 270 west, and tilt 0% would be straight down, and 90% horizontal, and everything in between will kind of give you some sort of isometric viewpoint. So here in this snippet, we get ourselves a camera from the view. So we get the current camera and we clone it. And then we use this cloned camera and just add 5 degrees to its heading. So we say turn a little bit more to the right. And then we take this cloned camera and assign it to the camera property of the view. And what this will do is will change the viewpoint for us. So let's do that. So I click once, twice, 3 times, and you see how we go towards the right in 5 degrees increments. So in order to move the camera to a desired position, in a smooth transition, we can use the go-to method, which has a number of ways that it can be used. In this case, we do the same thing as we did before. So we take a camera heading. This time we don't clone the camera because we don't need to set it, but we read its current heading at 30 degrees. So we go to the right, and then we use the view go-to method and tell it that we want a new heading, and we give it an option, which in this case speed factor tells it how quickly it should get there. So let's execute that. You see that we turn to the right 30 degrees one more time. We can also use it in a different way, where we just give it the coordinates of a special mountain in Japan, and then tell the view to go to that new center at a specified zoom level of 13. Let's execute that, and you'll see we'll fly across the globe to Nippon and to their famous Mount Fuji. To facilitate user interaction with the scene, we need a way to translate a screen point, so a coordinate on the screen, which, as you might be familiar with, is like something between 0 and, I don't know, 1024 and 0 and 678 in the old days. Nowadays with HD, we get much higher numbers. But to translate such a point into an underlying map coordinate, and this can be done with the toMap method. So what we do in this snippet here is we tell the view that we want to listen to a certain event, which is called click. And once that event is triggered, we want to drop into this callback. We get an event as an argument in that callback. And this event contains a X and Y coordinate, which would be that screen coordinate. And then we can tell the view that it should translate that screen coordinate to a map coordinate, and that will be the position. And then we can add a graphic with a cone symbol at that translated position. So let's do that. So you can see that when I click here, we actually drop a cone right there where I clicked. Let's click on this lake. Yep. So to allow targeting less performant devices, like for example mobile phones, we can instruct the SceneView to reduce its memory and performance footprint. Then we can use the quality profile and quality setting on the environment's atmosphere to change the behavior, rendering behavior of the SceneView. So here we're looking at a scene of San Francisco, and let's toggle that to low, and you will see that we immediately drop the resolution of the base map down here. We drop the vertex count of the geometry and the texture resolution. Now let's get back to high just to show you that difference and see how the whole view updates, and we get a much higher fidelity representation of the same data set. All right, so to visualize attribute data, or for that matter, any desirable data that you would like to visualize, we can use pop-ups that allow being controlled programmatically. So here we use the same view click event again to trigger an event. And in this case, we extract the map point, which is also in that event already, and just give it to the pop-up. So let me click somewhere. So here we see that we get the long lat of this coordinate, or of this building, or of that building. We can also define how attribute data stored on the server should be visualized in a pop-up. In this case, we tell the layer that we're loading that we want to enable pop-ups on it, and we define a so-called pop-up template where we can reference server attributes and kind of build a representation of those attributes with text around it to our needs. So let's say I want to look at this yellow building. It tells me that this building has energy consumption of this attribute electric use with a score of 84, which is this attribute star score. So this scene is set up such that if I click on a transparent building, I will get the original representation, like all the attributes that we currently receive from the server in the default template representation, whereas these colored or white buildings will adhere to this particular layer definition since they belong to a different layer. All right, this brings us to widgets. Widgets are pre-built functional elements that can easily be added to your application. They offer a large amount of out-of-the-box functionality, like for example, a legend view in case you define a renderer that splits up your data according to specified instructions, or a layer list widget that just gives you a list of all the loaded layers, a search widget, which we'll look at in a minute, that allows you to search for a location, or a line of sight widget, which is an interactive widget that allows you to analyze certain occlusion paths in your scene. We'll also take a look at that in a minute. So adding a widget is just as simple as adding a layer. So we load our preamble here, the snippet that we've seen a couple of times during this presentation already. And then we create a new widget, a new snippet, new entry here, which is that search widget. We give it the view that it should be attached to, and then we add that search widget in the top right position of the view. And lo and behold, it's in the top right position here, and I can enter some string, and it will search for that representation, and if I click on it, it will move the view in the direction such that the search result is centered on the screen. All right, this concludes our brief tour of 3D concepts of the JavaScript API, and I would now like to show some of the new features that we are shipping with the upcoming 4.15 release. Amongst them, 3D editing, integrated mesh draping, and the aforementioned line of sight widget. So editing of existing and creation of new data is one of the core capabilities of GIS applications. And we are proud to offer this in the web as well now. So here in the snippet, we're loading a particular scene with buildings and trees. And let's say that we want to add a feature here. So we want to add a line. Let's say this line goes below the bridge and then kind of follows in rough terms this curve and then joins the street. And now we have that line, and let's add it. And I could also edit this feature that I just added and edit single points and move them up or down. Let's move these up a bit since we're kind of trying to build another ramp here, maybe something along those lines. And the points that I'm editing will be stored as a line representation on the server, and if the next user comes along, he can see the result of this editing process and continue editing if he has the permission to do so, or just explore the data that I created while editing interactively in this scene view. So next feature that we would like to show is integrated mesh draping. And integrated meshes have become a valuable tool to process large-scale aerial survey data into an embedded visualization that augments like classical satellite imagery. And using these integrated meshes as ground replacements is now supporting draping as well. So here we have this integrated mesh is provided by Icon, and they surveyed the Yosemite Valley here, and you can see that we kind of have a in-place replacement of the classic satellite elevation data, which is not satellite, but I chose topographic base map here to highlight the differences a bit. And with integrated mesh draping, we can now add a polygon, for example. You can see how the line is already draped onto the integrated mesh. And I can say, oh, this area here is critical. We need to survey that. We might be looking at a landslide or something similar, and I can move to the area. And it behaves just as if I would have drawn that polygon onto solid ground, as if this integrated mesh wouldn't have been here. All right, last but not least, we created a tool that helps analyzing possible occlusion along lines, helping you to better understand the 3D data and analyze possible problems with like evolving scenarios. So in this example here, we have these orange buildings, which are part of a new development. And let's create a line of sight analysis. Let's say I'm sitting in this tower here and I want to look at the river and see how this new building influences my visibility to the river. Let's create one more point. So you can see that we have green and red parts. The green parts are fully visible, whereas the red parts represent the occluded sections of those lines. And if we toggle that new development layer, we can clearly see how this new building would influence a potential observer in that tower where I place this observer. You can also move it up a bit. So if we were to be higher in that tower, it wouldn't be that bad, obviously. All right, this concludes my section of the 3D JavaScript API concepts. Thank you so much for tuning in, and have a great day.